Hello everybody and welcome back to the Rubberduck Developer YouTube channel. My name's Daniel. I'm a consultant with a very strong software development background, and as always in this channel I'm going to talk about some maybe more advanced software development topics that just pique my interest. So the topic that I want to talk about today is in the area of secure software development practices. Namely, I want to talk about DLL hijacking. Based on recent conversations, I feel that not as many software developers who should know about that and know what it means, how it works, and which coding practices we have to keep in mind in order to prevent it. So what I want to cover in this video is a quick overview about how DLL hijacking works, what it is, making it a bit more understandable to you. I'm going to do a coding demo where I want to show you a insecure application and how a DLL hijacking can happen there so that you understand what the attack vector is. Then I want to go over some basic practices on what we can do in order to prevent that. And although I'm going to use C++ in that video, just be aware that any language and any operating system where you can dynamically load libraries can be affected by this attack. So even if you're using Java, the same thing that I'm going to show you with DLL files could in theory happen with jar files. So it's worth watching even if you're not a C or C++ programmer. So let's get into the conversation. Let's start by taking a look what DLL hijacking actually is, and what happens when somebody hijacks your DLL. So let's cover what happens when we load a library, or why we do that. So usually, you as the user are going to use some kind of application. It may be a text editor or it may be a sophisticated system. Whatever you're doing, usually these software systems, as you may know, are consistent of multiple libraries that they use to execute their functions. These libraries may be just standard libraries for opening and writing to files, or excise lower level operating system functions. They may also be a bit more higher level things that you have written yourself for your application, like encoding or decoding data, or talking to some kind of server, like you would have in this example. So there we have an application that uses a specific library that we created that will talk to our backend to perform some operations or just encode the protocol. For a DLL hijacking, what basically happens is that some malicious attacker gets access to your system and replaces one of the libraries your application uses with a library that they injected with malicious code. Once they have done that, they are basically in the position to execute any code they like whenever your library is called. So in this example, if we get access to a system and replace a library for communicating with a server, we can basically intercept anything that happens whenever the client or this application would be talking to the server. So what can I do once I'm in that position? Well, I can virtually inject any code. A common scenario is that I may redirect whatever you want to send to the server to my own server to grab your data. This is a classic man-in-the-middle attack. Suppose you're sending login data or credentials there, or some instructions for machines to do something on that server, and I can intercept them and I can basically access everything, and you wouldn't even know that this is happening because from the point of view of the application, everything may be working fine. And another thing that I could do is, and that is what happens very often, is I could run my own code. Suppose you're loading that library, and just when that library is loaded, or the library that I injected is loaded with the application you're using, I can run any arbitrary code. I could install my own rootkit. I can turn your application or your computer into my own botnet or mine cryptocurrency on there, and basically I can take over your computer that you're using just by injecting some arbitrary code into a library. Now you may wonder, is DLL hijacking actually something that happens? Is it a real threat? Well, let's talk about some examples. The ones that I show here are just randomly picked, but they should show you that even or especially big known software is more likely to draw such an attack. Like a couple of years ago, Nvidia software was infected by it, or even Microsoft software is commonly infected. Just imagine that I can manage to inject my own malicious code into a library used by Outlook or OneDrive. I may get access to all your emails. I might get access to all your files on OneDrive, and whenever you interact with the files, I can intercept that or do my own stuff and then replicate through OneDrive. And as you can see, even software protection systems like Microsoft Defender have been targeted of such attacks. And even open source projects like curl has been, a couple of years ago, a very prominent attack of a library injection. A rather big example was the library injection with Java. They actually used a file, java rmi.exe, that shouldn't be in the deliverable but was due to a release bug. And it was there for a long time. They attached to that, and whenever you started your Java runtime, they could get access to whatever was happening. So yeah, I think DLL hijacking is something that you should know of. Let's take a moment to talk about how DLL hijacking works on a lower level. So we've seen the high level overview on how I replace a library and then inject my own code, but how do I get there? So there are two lockpicks, as I call it. So the first lockpick we have to understand is how dynamic libraries are searched in the system. And so the first ingredient that we have is an attacker inject or replaces a dynamically loaded library in the operating system search path. What does it mean? So when your application starts, your operating system will look for specific DLLs that you load in the code in specific directories or specific places. On Windows, there's a basically hard-coded order how that works. Windows will first search in the application directory where your application is located, so where you have your exe file. Then it will take a look at the system directories, that's Windows/System32 or Windows/System, where it will look for them. And then Windows even goes so far to just search anything that's in your path for a matching library. And the first one that is found in this hierarchy, and that one will be taken and dynamically loaded into your application. You may think now, well, that's a typical Windows thing, but it's just marginally better on Linux systems. They're not DLLs, they're SO for shared objects. That's what the file type is called. But it goes into a similar direction. Most distros first go to the application directory. If they don't find it, they default to a path from an environment variable like ld_lib path. And then if you're using that in your system, there's a service called ld_config. Then that might infer some additional rules how libraries are checked. One thing we have to understand is that if we place a library in a higher priority search path, ours will be loaded. So just imagine somebody is using like WinSocks or the C or C++ library I would use to create socket connections. Then when you dynamically load that, it won't pick the library from System32, but it will pick the one in the application directory and use that. And if I inject some arbitrary code there, I'm already in your application and my code is running with the privileges of your application. So that's the one path. We have to understand DLL hijacking requires us to put our own malicious library in a higher ranking DLL search path. The second lockpick that we have is abusing missing libraries. So some applications may try to dynamically load libraries that are not actually there. Imagine stuff like optional libraries or plugin systems. Like you may have an application is relying on, let's say, a SSL library or an encryption library that you package with your application. But if it's not there, it may just not offer any encryption features. That happens very often. So in that case, your code may try to load the library. If it can't be loaded, we deactivate some features. But now what happens if the library is actually not there, but as an attacker, I go there and put a library with the right name and the right method signatures there. Your application loads it, executes my DLL entry, or even will use the functions that I provide through that interface. And then I suddenly have access to something without modifying anything. So if you're using a mechanism where your software tries to load the library, and if that's missing, well, just picks another one, you're opening an attack door. How might one find that out? So there are pretty simple tools that are open to everybody. This is a screenshot from the process monitor or ProcMon, which you can just download from Microsoft, that allows you to inspect different file events or different running processes. And I have an application here that I will show on later that's called Vuln for vulnerable. And this is an application that just has a bad file loading practice or a bad DLL loading practice. And I can just search there, and the search parameters were pretty simple. I knew that I was looking for that application called vuln.exe. And then I was searching for DLLs that couldn't be loaded. And then it just put out that list here. I specifically filtered for mylog DLL, which is a DLL that this application tries to load, but it isn't there. So I can see, okay, I just need to replace that one, and then I'm in the system. So let's draw that a bit together. How does the DLL hijacking attack usually work through? And let's combine the log picks together. So step one, if we want to run this attack, is we have to get hold of an application that we know the target may be using. Once we have that, we have to do a bit of analysis of the application, like identify where it tries to load libraries from, maybe if there are any missing libraries, anything that makes it easier for us. And when we figure out, well, it's loading that specific custom library.dll from that path, we already know where to go. The only thing that we then have to do is figure out what's in that library, and we can do that through DLL explorers or decompilers, and figure out which functions they provide, and then we can just write our own wrapper, use the original library, and act as a man in the middle. Once we have our own evil injected malicious library created, we just need to figure out which library path on the system that our target is using has priority. Like on Windows, it could be pretty simple. If we can get access to the application directory, we just put that stuff there and we're in. On Linux, we may have to do a bit of guessing or run from some identification scripts to figure out what we should do. But we have to keep one thing in mind here. Very often the DLL hijacking attack works from a point where we already have at least limited access to a user's file system. But then there are also other instances where we can just inject that library into, for example, a download package. As a reminder, there was just a couple of months ago a very meticulously designed attack. People recreated the Python website. They even offered you the download of Python 3. But when you downloaded it, you got a version that had such injected libraries. And once we found a way to get that library to the path, well, the only thing that's left is put the library there. I can offer you a download of, as I said, Python, where I just injected one of the libraries with my own code. You would install it and it would be there if we're not securely loading. Enough of the theory. Let's do a bit of coding and let's simulate a DLL hijacking attack. Let's take a moment to talk about my setup here. The code that I have here is in a GitHub repository that I will link in the description as well, so that you can look at every step. The code that I have is fairly simple. It is a C++ application that, as you can see, loads a library called mylog.dll. And yes, by the way, that code is running on Windows because it's easy to simulate it there. So we load this library mylog.dll. If we can't load it, we will print an error message. If it can be loaded, place a log output there, the application is running. Or if we can't find it, we would print we can't find the log function. So there are already two indicators. We are not completely insecure because we are checking whether we can load the library at all, and we're checking whether the function that we expect is there. Let's take a quick look at the other files in here. So we have one version of the library called mylog.cpp. You can see it just provides this one function, and the only thing it does is it prints info, colon, and then the message. Like, this could be a real-life logging library that we, for example, distribute through multiple applications in our larger software bundle to do unified logging. So quite a simple and quite a very realistic setup. I'm using mysys2 here because I'm on Windows, but I want to compile it with Clang. We're going to compile our application code. And just a moment later, it is already there. We can see we have the vuln00.exe here, and if we execute it, it will correctly tell us I failed to load the library. Okay, so let's also compile the library. The make target is called goodlib, so we put make goodlib there, and it puts a mylog.dll in the same directory with our exe file. And if we now execute vuln00.exe, we can see it prints info, the application is running as it called our function. Cool so far. Let's now inject our own evil malicious code in there. There is a version of the mylog.dll which I called mylog-evil.cpp, where you can see it implements the same function, log message function, with the same signature. So the API is compliant to what we're looking for, and it even would do the same thing. So we wouldn't see something going wrong here, but it has some malicious code injected here, which is simulated in the sense that everything that we put in there is written to a log file. Let's compile that. It's called, the make target is called make evil lib. We run that. And what it does, it replaces our mylog.dll with our injected version. And if I now, as you can see, if I now execute vuln00.exe once again, we see on the surface, we see the same software behavior. It tells us the same thing, there's no different behavior, but it also created a file called stolenlog.logs.txt. So cat stolen logs.txt, make that a bit bigger, where it siphoned the same log output there. So this is how we would inject. What did we do? Quick recap. There is an insecure application that just loads the library, calls the function, no checking involved. We replaced it with a drop-in replacement that just does something malicious, and then replaced the DLL files. And we could see that our application didn't care. It didn't recognize, and so we maybe couldn't recognize. In reality, if this would be, for example, high performance setup, you may notice that something's wrong because there may be delays suddenly, or there may be disk I/O happening that you didn't expect. But that already requires very strong monitoring on your software. So first things first, let's be clear, what I just demonstrated, that's an engineering problem, right? That's not some far-off cybersecurity hacker stuff. This attack is only possible because we made some grave errors in how we deal with our dynamic libraries and how we load them and how we treat them. So the vector of the attack is a badly coded application. So now what do we need to be aware of with our application? What can we do? I have 4 core practices that I would advise everybody who is loading DLLs dynamically advise to use. So the first one is, instead of just loading the application in a relative path, use a fully qualified path. So that if I show you the code again, that means don't do it the way we do it here. Just write a mylog DLL, because that will prompt the operating system to just find that file. Instead, use a fully qualified path telling it exactly where to look. Yes, this means that you may have to be a bit more prescriptive in how your application is set up and installed, but that's worth it. The second part is, or the second practice that I advise you to do, is verify your loaded libraries. Don't just only check if it's there or if the functions are in there. Include things like checksums. Figure out if your library was modified. A very simple way that I will show you in a couple is to, for example, use MD5 during the build process to figure out what the MD5 checksum of the loaded library should be, and then before you load the library, run the checksum and just fail your application if it doesn't load. This helps you to ensure that the library is the one you're expected during build time. The third thing that you should do is use digital signatures. So especially on Windows, it's very, very easy to use the sign tool that ships with the development environment that Microsoft provides through, for example, Visual Studio. It allows you to add a digital signature to libraries or binaries in general, and also verify them, especially during the build process. Also check if you are using the right libraries, the one that you're expecting, and if something's off, investigate. Don't just blindly update and accept it. And the fourth practice that I encourage, this is on the one hand not something that you can do while coding it, but that you can advise your users to, is that they should enable the Safe DLL search mode registry flag. That takes an influence in the order of libraries processed or library search paths processed. Instead of having the application directory as the first one, it prioritizes the system's actual system libraries over the ones in the working directory. If you're using Linux, you can use ldconfig to set that up correctly. So in my point of view, taking the stuff from the actual working directory should be the least priority. And that also means that you should not use stuff like set DLL directory in your code, because that would disable that setting of the operating system again. So that's a secure coding practice here, and the other one is encourage your users to enable that. Let's take a look on how we can change the application to do that a bit better. So this is how we start out here, and the first improvement that we can directly do is use a full path instead of mylog DLL. So in that case, I know where it will be located. I can tell the system to use the folder that I have here, like it's just in my home. I have a projects folder, and there's something called DLL Hijack, HJ for hijacking. And let's say it has to be the libs folder there. Let's save that and open up the console to just compile that again. Okay, now let's take a look here. There is no libs folder, as you can see, but we have mylog.dll in the folder. But if you run that now, our vuln00.exe, we'll see it now tells us failed to load DLL, because it is specifically looking for this path. So if we now create the libs folder and move the mylog.dll to the libs folder, so I can see it's no longer in the working directory, but it is in the libs folder, and we now run vuln00.exe, oh, now suddenly the application is running because it found that library on that path. It doesn't search anywhere else. If it doesn't find it on the fully qualified path, it won't tell you the application, that the library is not there. So that's the first thing we can do. So that's the first practice we included here. I'm going to code it here. Practice 1, use the full library path. Cool. So the second thing that we can do is including a checksum when loading the library. This is fairly simple. I implemented a version of calculating the MD5 checksum. You can build that with make MD5 sum if you're using my code. And the reason why I use my own implementation or a separate implementation here is, yes, of course, we could use the OpenSSL implementation, but just to be aware, that again means we load a library into our application if we don't statically link it, and then to compare that. That again opens a bit the door for an attack vector, so I decided to just include my own hashing algorithm there. So if we run make MD5 sum, it creates a small MD5 sum.exe here that I can run on any file. So if we now in our build process build the library where everything is fine, and we run MD5 sum on my log.dll. Okay, so we get that checksum back. We are going to include a checksum calculation in our application here. So we can bake that good checksum in here. I just do that through a very basic define. I know that's not best practice with CPP, but just imagine during the build process, we can, for example, write a header file that does that, or we can just include it in our code. And if you would take a look at the make file here, if you would run the make vulnerable 02 target, it will do exactly that. It will create a checksums file that will be used in that example. So we calculate the checksum from our library, from the library that we know is the right one. We include that in the code. So we declare the function here. Now we have the library part, the library path configured in the variable, and now what we can do here is call the MD5 checksum function, which expects a library path, and we can just say, and can compare that with the good checksum we have above. And if that does not equal 0, we can just write an error message there like library was modified. We save that. The only thing that's left to do there is to include string up here. If we now go there and compile our application, once again we have to include the md5.cpp here, of course, because that file defines the hashing function, and we make a libs directory and build our good lib and move the mylog.dll to the libs folder. Let's see what it tells us. It tells the application is running because everything's fine. The right library was loaded. Now let's see if our security changes really helped us, because now we're going to build the evil lib once again. Just keep in mind that creates a stolen logs txt. I just built it, and now I'm going to move to mylog.dll, which is the modified version, to the libs folder. And if I run that application now, it tells us the library was modified. So if we don't want this to just be a warning, of course, we should here end with a error code. I just put some arbitrary number there. We can rebuild the application. You can see we just exit with the library is modified. And the important part here is, and you have to keep that in mind, that we have to run, of course, the checksum before we load the library, because as soon as the library is loaded, there may already be some malicious code executed. So just read it, test it, and if it's fine, all is good. So let's take a moment to summarize for a moment. So DLL hijacking basically means that an attacker gets access to your file system or somehow to binaries you're using and replaces an existing dynamically loaded library with one that was modified to execute malicious code. We've seen that this is possible to either attack through, for example, with plugin system, through missing libraries or optional libraries, to just place them there and then on execution run something. And it has to do with placing the libraries that they want you to use, so their malicious libraries, into a higher priority search folder. Matter of fact is that DLL hijacking happens if we have bad coding practices, and we can easily get rid of that, or at least add an important layer of protection if we verify the libraries and tell the dynamic linker which exact path to pull them from, and this just minimizes the attack surface. And this is something that everyone who writes applications using dynamic loading should do. So if you're writing code that just uses load library or something similar in your programming language or setup, please go there, implement at least a fixed path loading and a checksum validation to make sure that you are not the next victim of turning your users into botnets. So with that said, I hope you have a great day.